let's continue now. I'm recalling some basic facts in field theory, and in the last video we ended with this multiplicative property of degree of field extensions. So let's continue. I'll recall some other important things about field extensions. So let me just quickly talk about field homomorphisms first. Field homomorphisms are really nothing but ring homomorphisms, right? So a field is a ring, and a ring homomorphism is one which preserves the addition, multiplication of the ring and sends 1 to 1. So it must send 1 to 1. I'll recall only that, but there is nothing additional for a ring homomorphism that you require in order to be a field homomorphism. What we are more interested in is the following. So let K over F and L over F be two extensions of F. So you have K, L are both extensions of F. Okay, we can consider homomorphisms from K to L that just completely disregards F and just treats them as two rings, and you look at a homomorphism. But an F homomorphism of extensions of F. So if you take two extensions of F and you want an F homomorphism, is a field homomorphism sigma from K to L. So it is a map from K to L, a field homomorphism, in other words a ring homomorphism. But in order to be F homomorphism, it must have further the property that sigma of A is equal to A for all A in F. Okay, because F is a subfield of K, if A belongs to K, A belongs to F, it's also an element of K. So you can ask for what is sigma is. Sigma of A is an element here. Okay, but F is a subfield of L also. So that must equal A. Okay, that is the requirement for it to be an F homomorphism. Okay, so just to give you an idea, so this is in fact an exercise for you. If K and L are field extensions of Q, then any field homomorphism is a Q homomorphism. Okay, so this is an important exercise. It's an important exercise for you. It says that any element of Q automatically is fixed by sigma. So that's what, remember, this means. So this means sigma fixes. So we will remember this condition as saying that sigma fixes. This terminology will be useful for us later. So F homomorphism must fix everything in F. So A must go to itself. So here any field homomorphism we know fixes integers. So actually first it fixes 1, so it fixes every integer, then it fixes this. Okay, so that's the hint. I will not go into details of this. Okay, so that is an important, so there is nothing extra for it to any homomorphism of field extensions of Q to be Q homomorphism. It is automatically a Q homomorphism. On the other hand, let's take K to be Q root 2 root 3 and L to be Q root 2 root 5. So Q root 2 root 3 is the smallest subfield of, let's say, R containing Q root 2 and root 3. L is the smallest subfield of R containing Q and root 2 and root 5. So if you consider the map from K to L, which sends root 2 to minus root 2, so here I should have I'll take k to be this itself, L to be this itself. Okay, so and root 3 to root 3. Okay, so sigma, this is an exercise for you. Sigma is a field homomorphism. So check this. This is the first exercise. So it is a Q homomorphism. Okay, and note that you have K equals L. So K equals L. Maybe I'll write this separately here. K, L are sitting above Q root 2 and this is sitting over Q. So this is, let's say F is this. So and this map is sigma. Okay, so that is a picture. So this sigma is a Q homomorphism, but sigma is not an F homomorphism. This is clear because it doesn't fix root 2. It doesn't fix root 2. On the other hand, if I introduce a new field here, F prime, so let's say F prime is equal to Q root 3. Okay, so the third exercise is that sigma is an F prime homomorphism. Okay, so F prime sits here. They're both things over F prime, but it is an F prime homomorphism because root 3 goes to root 3. Okay, so this is just to give you an idea of what field homomorphisms are and what field homomorphisms or field extensions are. Okay, so now the next topic I want to discuss is very important. This is really getting to the crux of the subject in Galois theory, is adjoining roots. Okay, so I'm going to state a big theorem here which requires a little thinking. It's not difficult, but this is done in any field theory course. Okay, so what I want to say is that let F be a field and let Fx be a polynomial over that field in one variable. Okay, so the theorem is there exists a field extension K over F, K of F, such that F splits as a product of linear polynomials in Kx. Okay, that's all. So the theorem is very important, not difficult to prove, but I will not tell you anything more than just give you a hint of how to prove this. But before that, I want to introduce an important example. I mean, this is illustrate this by an example, because essentially this is going to be clear if you know what, if you look at the right example. Let's take x square plus 1 as a polynomial over q. Then you can take k to be c, right? Because x square plus 1 does split as a product of two linear polynomials. Okay, k equal to c works, but k equal to r does not work, right? Because x square plus 1 remains irreducible in Rx, so it doesn't work. You don't need to go all the way to c. Q adjoint I also works, right? So the interesting thing is you have Q here, R here, C here, doesn't work here, it works here. Okay, but you don't need to go all the way up to C. It's an infinite extension of Q. You can take Q adjoined I, in this it works. Okay, so this is the theorem is saying that there is always an extension where the polynomial splits as a product of linear polynomials, means degree 1. Linear means degree equal to 1. That means it has all the roots there. X square plus 1 doesn't have roots in rational numbers or real numbers, but it has roots in C, but in fact it also has roots in a much smaller field Q adjoined I. All the other things in C are irrelevant for this particular polynomial. You need Q adjoined I only. And all I will do towards giving you an idea of how to prove this theorem is the main step of the proof. So suppose F is irreducible. Consider K to be Fx modulo Fx. Then this is a field extension of F. So what you have is K, which is defined as Fx modulo F, is a field extension. This is trivial because you have F to Fx and you have a surjective map by the standard properties of ring theory, and this I am calling K. So now this map is not injective because there are polynomials which go to 0, namely Fx itself. But this map is 1, 1 because F is a field. So F is a subfield of K, so this is a field extension. And further, X bar in K is a root of Fx. Okay, so we can write Fx. So in Kx we have, because X bar, so let me call this element, let's say alpha. X bar is an element of K, so let's call that alpha. Then Fx is nothing but x minus alpha times gx, and degree of g is of course strictly less than degree of f. So we proceed by induction. So we have essentially added one root for an irreducible polynomial. Now to prove the general statement, you first look at f, you look at its irreducible factors and work with them separately one by one. And once you have an irreducible factor, you adjoin one root and then you reduce the degree, so you can proceed by induction. So this is a very important theorem that will be essential in Galois theory. Now I am going to introduce this very important notion of splitting fields, which is related to the field K that we constructed above. So this is the following. So let F be a field. Okay, so let F be a field, and let's take a polynomial in capital Fx, and let K be a field extension such that F splits into linear factors in Kx. Okay, so just to avoid writing this entire sentence here, splits into linear factors, I will express that as splits completely. Okay, splits completely means you can write, if f has degree 10, there will be 10 linear factors, maybe repeating, but there will be 10 linear factors. So now such a K exists by the previous theorem. Right, such a K exists by the previous theorem. Now as this example here of C for x square plus 1 showed, maybe we are doing too much in that field. Maybe there are lots of unnecessary elements and we don't need those. So this is the following. So now a splitting field. Okay, so before I define that, so let's say let alpha 1 through alpha r, alpha n, let's say, be all the roots of f in K. Okay, in other words, what we are saying is that fx splits completely as x minus alpha 1, x minus alpha 2 times x minus alpha n, and this holds only in Kx. So then the subfield F adjoined, alpha 1 through alpha r are clearly algebraic, so I can use square bracket or round bracket, is called a splitting field So the full sentence is important. Splitting field of fx over f. Okay. Splitting field of fx over f. So just take the smallest field containing all the roots. Then it's called the splitting field. And then there is a fact which is that any two splitting fields any split of a polynomial fx over f are f isomorphic. Not only are they isomorphic as f extensions, but not only are they isomorphic as fields, they are isomorphic as f extensions. So that means if k and l are two splitting fields, then there is an isomorphism as f extensions of f. That means there is an isomorphism of fields which fixes every element of f. Okay, let me quickly give you some examples. So obviously splitting field, so maybe I'll write, so examples, splitting field, so I'm going to write this as sp.fd in short, of x square plus 1 over q is q adjoined I. Right, so and I'll write degree here. Degree of the splitting field is 2, right? So splitting field of x square plus 1 over q is qi, because you can take C where the polynomial splits completely and you just adjoin the roots which are I and minus I, so adjoining I is enough. What is the splitting field of x square plus 1 over r? Actually this is nothing but C, so this is r adjoined I. So the degree is still 2. What is the splitting field of x square minus 1 over q? This is actually just q itself and the degree is 1, because here roots are 1 and minus 1, they are all already in q, so you don't need to add anything more. What is the splitting field of x4 minus 1 over q? So in order to do this, we have to figure out how this splits. This splits as x plus 1, x minus 1, x plus I, x minus I, right? This inside Cx. In Cx, this is how it splits. 1 and minus 1 are already in q. So if you adjoin I, minus I will already be there. So this is q adjoined I as before. So the degree is 2 here also. And finally, I'll do one example. This requires a bit more thinking. What is the splitting field of x power 8 minus 1 over q? So here x power 8 minus 1 splits as, these are roots of this are 8th roots of 1. Okay, so clearly 1 minus 1 I minus I will be there, right? But there are more, and this is some complex number. If you know, these are elements on the circle, right? So these are primitive. This is a primitive nth root of 8th root of unity, and this, if you recall the formula, this is cosine pi by 4 plus I sine pi by 4. So this is 1 over root 2 plus I times 1 over root. Okay. So now you can check that if you adjoin I already, so 1 over root 2 will be there. So one can check that 1 over root 2 will be there. So the splitting field is just I comma root. Okay. So this part is an exercise for you. So the splitting field is exactly 1 over q adjoined I comma root 2, and the degree is 4 here. So the degree of the splitting field is 4. So as you can see, degree is something smaller than the degree of the splitting field is some number which is less than or equal to the degree of the polynomial. Here degree of the polynomial happens to be equal to the degree of the splitting field. Here degree of the polynomial is strictly more than the degree of the splitting field, and so is this in this examples. Okay, so the entire Galois theory is really about studying splitting fields. So I'm going to, when I start proper Galois theory next time, I'm going to spend a little bit more time on splitting fields and introduce new concepts there. So this is just to give you a basic idea of the definitions of splitting fields. And the final topic that I want to do in the review is finite fields. Talk a little bit about structure of finite fields. Okay, so a finite field, as the name suggests, is a field which contains only finitely many elements. Right, so the primary example for us is Fp, which is by definition Z mod Pz. The order here is P. So some important observations about finite fields. Characteristic of a finite field is greater than 0, right? Because remember, I recalled the characteristic. You have a if F is a finite field, so let F be a finite field. In this rest of this video, F is a finite field. There is a homomorphism. The kernel has to be non-zero. Because if the kernel is 0, Z will be contained in F. Z is infinite, so F will be infinite. But F is finite, so kernel will be non-zero. It is generated by a prime number then. So characteristic is in fact a prime number. And if characteristic, further we have, if characteristic of F is P, let's say, then F is an extension of Z mod, so let me write as a Fp, right? Because that is clear, because the kernel, say kernel is Pz, so this gives me, by the isomorphism theorems in rings, an inclusion like this, and this is nothing but Fp, right? So F is an extension field of Fp. So now if you look at this degree is going to be finite, obviously, right? Because F itself is a finite set. So there is a finite basis. So this is a finite extension. So let's say n is the degree. Then a simple counting calculation shows that, then simple counting shows that cardinality of F is actually P power n. Because there is a basis consisting of n elements, so all elements of F can be obtained by putting some coefficients in front of the basis. So for each basis element you have P possibilities, because the coefficients have to come from Fp. So there are P possibilities for the first basis, P for the second basis, P for the third basis element, P for the nth basis element. So altogether you have P times P times P n times, namely P power n elements. So in conclusion, a finite order of a finite field has to be P power n for some prime P and positive integer n. Right, so in particular they can't be a field of order 6. Right, because 6 is not a power of a prime number. You have to take a single prime, whereas it can possibly be 8 or 9 or 16 or 25. So we have only showed that if you are given a finite field, its order must be P power n. Now the question is, given a P power n, is there a field of order P power n? and this is expressed in the structure theorem of. So I'm going to write a series of facts about finite fields. One of them answers the question that I just raised. We may not need all of these, but I thought it will be a good idea for you to recall them before we embark on the study of Galois theory. So let P be a prime number and let R, I'm going to use R here, be a positive integer, set Q to be P power R. Okay, so then the following hold. The first statement is there exists a field of order Q. Okay, so this answers the question. Give me any prime number power a positive integer, there is a field of order Q. That means there is a field of order 4, there is a field of order 8, there is a field of order 16, there is a field of order 9, 27 and so on. Moreover, any two fields of order Q are isomorphic. In fact, over Fp. Okay, they are isomorphic over Fp. So they are both extensions, as I said. Any two fields of order Q are extensions of Fp. There is an isomorphism like this. Okay, so let K be a field of order Q. Then the collection of non-zero elements of K, K cross, is a cyclic group under, of course, the multiplication operation, this is a very useful statement that we might at some point use. Let K be a field of order Q. Then elements of K are roots of So K is in fact the splitting field of this polynomial x power Q minus x over Fp. It's very rare that roots of a polynomial form a field or even a group. It just happens that roots of this particular polynomial form a field of order Q. There are Q elements, it's degree Q, they are all distinct, one has to prove that, and they form a field. That's in fact how you construct a field of order Q. So a field of order P power R contains a field of order P power K if and only if K divides R. Okay, this symbol, remember, means that K divides R. This is my shorthand for K divides R. So only way that P power R contains a field of order P power K is K divides R. I will give you an example of this in a minute. And finally, this might be useful for us later. Irreducible factors of x power Q minus x in Fpx are the irreducible polynomial in Fpx whose order divides R. Okay, so this may not, if you recall this, that's good, otherwise you should go back and check this proof of this theorem. But these are the 6 facts that we learn about finite fields. Okay, so just to give you an idea, so example, how to construct a field of order 4. So notation is that for convenience, a field of order Q is denoted by this agrees with our notation of Fp, and it also is meaningful because any two fields are isomorphic. So we are permitted to use a single notation for any field of order Q. So up to isomorphism it is 1 only. So a field of order Q is denoted by Fq. So now what is F4? So F4 must be an extension of degree 2 because number of elements of F4 will be 2 power 2. So this is a degree 2 extension. And if you 0 and 1 are there always, of course, because 0 and 1 are here, but the new elements can be denoted by alpha and 1 plus alpha or 1 minus alpha, where alpha is a root of x power x square plus x plus 1. This is the only reducible polynomial of degree 2 in F2x. So that means elements of F alpha can be represented as roots of this, right? Because this is x times x minus 1 times x minus alpha times x plus alpha. I mean, this is how it is, but we factor this usually as first you do x times x cube minus 1, then you do x times x minus 1 times x square plus x plus 1. Okay, this, so I should really write this holds in F4x, not in F2x, because alpha is not in F2. This holds in F2x. And the point is, these are the three irreducible polynomials in F2x whose order divides 2. That is the last sentence. The irreducible factors of x power q minus x, or in this case x power 4 minus x in F2x, are the irreducible polynomials whose order divides r, in this case 2. Okay. So, and then a final example about the series of inclusions. So, if you take a field of order 3 power 12, okay, so it contains a field of order 3 power 6, because 6 divides 12. It contains a field of order 3 power 3, and this contains F3. On the other hand, you have also F3 power 4, but there is no relation between F3 power 6 and F3 power 4, because 4 does not divide 6. So you also have F3 square is contained in F3 4. F3 square is also contained in F3 6, because 2 divides 6. Okay, so there is any bar here represents an inclusion, represents a field extension. There is no bar, I mean, or a series of bars. From 2 to 12 there is a series of bars. From 2 to 6 there is a bar, but 2 to 3 there is no bar, because 2 doesn't divide 3. And if you want to write the degrees here, this will be degree 2, this will be also degree 2, because 3 square to that, this will be degree 4. And the entire degree of course is 12, 2 times 2 times 12, which we know. So this degree will be 2, this degree will be 3, and this degree will be 3. So you can go from F3 to F3 power 6 either like this, which is 2 times 3, sorry, and this is 2 I should write. So 3 times 2 like this, or 2 times 3 like this. Okay, so this is just a tree of subfields of F3 power 12. Okay, so let me stop this video here. This more or less completes the revision that I wanted to do, and from the next video we will start our study of Galois theory. Thank you.